Hello everyone, welcome back. Today we will understand the self-balancing technique used by red-black tree during deletion process. We know that red-black tree is a binary search tree. So before understanding the deletion logic in a red-black tree, let's quickly recap how the deletion is handled in a standard binary search tree. So whenever we delete the node in a binary search tree, basically we consider the three cases. Delete the node with no child, or whether the node which we are deleting have just one child, or whether it has two children. So in the first case, when we delete the node with no child, we directly delete it because it does not impact any binary search tree property. For example, here if we delete the 20, then it is not impacting any binary search tree property. Basically, for each node, the smaller values than that node are on the left side and greater values than that node value are on the right side of that node. So if we delete the 20, which was the node with no child, it did not impact that binary search tree property. So we can directly delete it. So basically, we are physically removing that node 20. In the second case, when we delete the node with only one child, the child of deleted node becomes the child of deleted node's parent. And no further action required because in that case also it does not violate the binary search tree property. For example, here, let's say we delete the 70, then 60, which was the child of deleted node 70, will become the child of node 70's parent, which is 50. So it is still satisfying the binary search tree property. But when we encounter the case to delete the node with two children, let's say node 50, which has two children, then if we delete it, then what we should replace it with so that the binary search tree property is still valid. So here how the binary search tree handles it, it finds the in-order successor for the node which we want to delete. So basically the in-order successor for the node is the smallest value which is greater than the value of the node we want to delete. So let's say if we want to delete 50, the in-order successor for 50, which is the smallest value greater than 50 is 60. Now, if we observe one thing, the in-order successor is basically either have no child or can have only right child. Why? Because let's say if 60 have left child 55 and right child 65, then for 50, the in-order successor will be 55, not 60, because 55 is the smallest greater value than the 50. And if let's say we have only 65, then in that case, in-order successor will still be 60. So it can have the right child. So the in-order successor can have either no child or just one child, which is right child. So what we do basically, we swap the values of node to be deleted and in-order successor. And physically, we delete the in-order successor node, not the node with two children. So we delete the 50. So in that case, if you see this deleting the node with two children actually becomes the case of delete node with no child or delete node with only one child, because we know that in order successor can have either no child or just one child. So this fact we need to keep in mind that physically we remove the node with either no child or node with just a single child, right? So considering this fact, and if we consider that in the context of red black tree, where we want to, we will either delete the red node or we will either delete the black node. Now, when we delete the red node, the two cases which we saw in the previous slide, we will either delete the node with no child or delete the node with single child. So red node with no child is possible. So this is the one case where red node with no child basically is the leaf node. But the second case where red node with just one child, it is not possible. Why? Let's see why. Because let's say if node 20 is a red node, it has just one node. Let's say its color is red, then it is violating red property. then this is not allowed. And the red node with just one child with color black, it is violating the black height property for node 30. So black height here is 1 and null 2, and here only 1 for null. So it is not matching. So it is causing black height violation. So the second case, which is basically deleting the node with one child, does not apply for a red node. So for red node, it is only one case, deleting the red node with no child. For deleting the black node, those two cases apply. Right? As we see, valid red black tree does not have red child for red node with only one child. So we can delete the black node with no child. It is possible to have a black node with no child. It is possible to have a black node with only one child, but that one child will always be red. Why? Let's say if we have like this, 20 is a black node with black child, then it is violating the black hat property for 20. So black hat property for 20 is, for this part, it is 1, 2, null is 3, here 1, and null is 2. So it is not matching. So it is not possible. So in a valid red black tree, there won't be black node with only one child, and that child color is black. So it is not allowed. So the two cases where deleting the one node or deleting the node with only one child or deleting the node with no child, if we map it with the black node, then we get this two cases. So overall, we need to handle these three cases for a red black tree deletion process to self-balance. Let's understand how these three cases are handled. Right? I hope you understood how we came up with these three cases, because in a previous slide, we saw that physically we remove the node with either no child or node with single child. And if we map those fact to red node and black node, we come up with this three cases. Now, first case, delete red node with no child. Let's say we are deleting 90 here, which is basically we are deleting the red node with no child. Perform the standard binary search tree deletion. Now node with no child is deleted directly. And it is a red node. So it does not impact any black height property or other property of red black tree. So it is fine. So deleting a red node with no child does not impact any red black tree property. So it is safe to delete. And we can directly delete. No further action required. So the first case is easy. Now the first case itself, let's try to understand with different example. So let's say we want to delete 70 now. Now one will think, here we are deleting the red node with two children. Then why are we not having that case? As we see, whenever we delete the node with two children in a standard binary search tree deletion, we don't delete that node physically. What we do, we find the in-order successor, and in-order successor here for 70, 75, we swap the values. And we know that for in-order successor, it can have either just a right child or it can have no child. So it is basically for a red node. If the in-order successor is a red node, it cannot have a single child in a valid red-black tree, because it can cause a red-red violation or black-white violation, as we saw in a previous slide. So again, this case gets related to this, right? So the in-order successor is red, then it becomes nothing but the case of deleting red node with no child, right? So initially we were deleting 70, which had two children, and how it basically maps to this case, deleting the red node with no child. Hope you understood this part, right? And in this case, we just now saw in a previous slide, we can directly delete this red node with no child because it does not impact any property of red black tree. So it is safe to delete. So the first case is easy to understand. Now the next case, delete the black node with one child. Now let's say we delete 70 here again. So what we do in a standard binary search tree deletion, we find the in-order successor, which is 80 here. We swap the values, and then we actually delete the in-order successor. Now here the in-order successor have a one child. Now in-order successor is a black. Now if the in-order successor is a black, Then there can be two cases. One is deleting the black node with no child, or deleting the black node with one child. Now here it is one child. And we know that if there is a black node with just one child, it will be always red child, right? So now let's say we delete 70, then 90 becomes the new child of parent of 70. So what we basically do, now if you see here, the black height is decreased on this path. But this case can be easily solved using recoloring. How? If you see all other paths have extra black node, right? 1, 2, and null is 3. Here it is not there. 1, 2, 1, and null 2. So 1 is lacking because we deleted the black node here. But we replaced it with the red node. So we can easily mark the red node to balance that height, right? So what we basically do, we deleted the node, and the child of that black node, which color will always be red, we mark it as a black so that it balances the whole tree black height, right? So this is also the case. Basically, whenever we delete the black node with one children, that one children will always be red. So now that red children will replace that black node, and we mark that red children to black so that it balances out the height. So this is also easy. Now the third case and the last case, right? Deleting the black node with no child. Now here, let's say we delete 70. The standard binary search tree deletion, we find the in-order successor, which is 80. We swap the values and we know that the in-order successor will get deleted, right? And if the in-order successor is black, then it becomes nothing but the case of deleting black node with no child or one child. If it is black node with one child, it will be always red, and we saw that in a previous case. So this is the case of deleting the black node with no child. Now the problem is, if we delete the black node with no child, what is the problem? See, if we delete the black node with no child, then it gets replaced with the null children. So it is basically, it gets replaced with the black node only, right? And it causes the height problem for this path. And we don't have any other node like red node in previous case which we can just do recoloring and fix it. Here there is no extra node. Here it is null. So whenever the black node is replaced by either black null or other black node, then it is called as a double black condition in a red black tree deletion process, right? So now if we delete 70, it will be replaced by null, which is again a black. So it is nothing but the double black condition. Now, if you see one thing here, if you delete the 70, which smallest subtree is impacted? This one, right? Because if you delete 70, the 80 is the black height for 80 will be impacted first. So this is the smallest impacted subtree. Now, this is the valid red black subtree in a red black tree. It is also eventually valid red black tree. This subtree is also valid red black tree. Because if you see for 80, it does not have any red violation. It is having proper black height. So it was a valid red black subtree. So depending on to the structure of this subtree, there are further cases in this delete black node with no child case, right? So how this subtree can be represented in a valid red black subtree? What are the different cases? So this, either it can be like this, where we are deleting the black node with no child. The subtree, which is the smallest subtree which can be impacted, can be like this. So this is one case. Or the smallest subtree which can be impacted can look like this. Or the smallest subtree can also look like this, one of this, right? Where the smallest subtree which gets impacted if we delete the black node with no child, either on the left side there is a black node with no children, or on the left side there is a red node with two children, So this is one structure, this is one structure, this is one structure, and this is one structure where on the left side there is a black node and other children of that black node are red. So this is one structure. So depending on each structure of that impacted smallest subtree, we have different cases to handle. So let's understand the first case. So if we delete the 70 node here, you can see this is the smallest impacted subtree. So X is the replaced node. So when we delete the node 70, the node which replaces the 70, in this case, null is replacing the 70. So that is called as X, and P is the parent of X, and S is the sibling of X. So let's say if X is the right child of parent, then the left child of the parent will be the sibling of X. Or if the X is the left child of the parent, then right child of the parent will be sibling of X. Now, this is the first case where sibling is black with no child or both black children, right? Now, this is the first case in this is the first subcase in a delete black node with no child. So what we need to do here, if we represent it in a big tree, it will look like this. So what is happening? So first we will try to fix the height problem for this subtree. How it can be fixed? Recolor the sibling to red. Why? Because if we do like this, and because there is extra black on this side, right? So, but here the red violation is coming, might come, right? So what we do to avoid that red violation, we change the parent red to black. Now, two things. One is it is fixing the red violation here, and it is also fixing the height at upstream, right? Because previously, if this was red, there was one black height was getting added here for the whole tree. Now, if we make this red to balance it out here, we are actually reducing the height at upstream. That's why we change the parent to black if it is red to balance that height problem, and it also solves the red violation. But if the parent is already black, right, then there won't be red violation, but the upstream side, we are basically, because we are making sibling red, then it will create the black height problem upstream. So here we fix the black height, but it will create the black height problem at 50. How? Let's say this is the example. We deleted the black node here. We basically mark the sibling as red because then it is the case 3.1. Sibling is black with no child or both black children. Now we fix the height problem here. But now we caused the height problem for node 50 because it was 1, 2, 3, null 4. Like that, it was 1, 2, 3, 4. But now it is 1, 2, and null 3 only. So we caused the height problem at upstream. So we need to fix this upstream. So what we do, we basically consider this P as X, new X, and continue to fix till we reach the root, right? Now X, till we see the, basically, till root we continue to fix, right? Now X sibling is black with no child over here. Both the children are black. So what we do, we make the sibling red. Parent is black, but it is root, so it is fine. So we don't need to continue to fix up above. So you can see it actually fixed the black height property for whole tree. 1, 2, null 3. 1, 2, 3. 1, 2, and here null 3. So it fixed everything. So this first subcase in a delete black node with no child, where the subcase is if the sibling is for the X is black, for X if the sibling is black with no child or both black children. So it can be easily fixed using recoloring. And that recoloring we need to basically continue to fix up above till root. In some cases, we might need to do that. Now the next structure, right? See, the thing is here we are deleting the right children. That's why the structure is looking like this. But if suppose we are deleting the left children, then the structure will be basically the mirror image of this. So the structure is same, just a mirror image. But we are just considering in the context of deleting the right child. So if we delete this, then the tree will become like this. This is the X, basically the null node which replaced the node 70. This is the sibling of X, and this is the parent of X. So now the case is sibling is red. Previous case was the sibling is black with no child or basically both black children. Here the case is sibling is red and no child or both black children. Now sibling is red, so it is already red. So we can't recolor. We can't do anything here. And we can't mark parent as red. Because if we mark that red, then we are actually creating height problem. We are not solving the height problem here. We are also creating a height problem for upstream, right? So simple recoloring will not work here. So what we need to do, we need to, because sibling is red, so there is a possibility to make the sibling black to fix the black height for this subtree. But we can't just mark it black here, right? So we need to bring this sibling up. So now how to bring it, right? So if the sibling is the left child of P, then we need to do right rotation so that the sibling will come at top. If the sibling is right child of the P, then we need to do the left rotation. What is left rotation and right rotation? That we have understood in detail in our previous A-Will tree and red black tree videos. So please go and check it out so that you will understand the details mentioned in this video. Right? So the right rotation, because sibling is the left side, the left child of P, so we need to do right rotation here. So we did the right rotation, good. Now in the right rotation, for the new parent or for the new parent, if there was any right subtree, then it becomes the left subtree of the old parent, right? So that is the standard right rotation at work. Now, did we solve the problem? Here, if you see 1, 2, 3, black eyed 4, null 4, here we didn't solve. So what we need to do? We basically change the sibling to black so that all the paths which are coming from the sibling will have that black node considered, and it will try to basically balance the black hat for upstream tree. So we change the sibling to black but and old parent to red. Why old parent to red? Because there is more black here, right? So we need to make old parent red. Now the problem is if there is here, if there was any child for 65 was a child of 60, so it became the left child of 80 after right rotation, and it was black, right? To handle now, red child cannot have just a single black child as we saw in the previous videos. So it basically now becomes the case 3.1, right? Case 3.1, which we discussed. Basically, sibling is a black with no child or both black children. So this is this case one, which we can easily fix. We can make the sibling red, and to avoid this red-red violation, we make the parent black. Now you can see the black height for whole tree is fixed, and black node with single red child is allowed. So this is now the case 3.2 is fixed, where we are deleting the black node with no child, and sibling is red with no child or both black children. Now coming to the next subcase of delete black node with no child, next structure. Here we delete the black node. Now black node is deleted, it is replaced with null, which is also black. So it is a double black condition. So for this case, we always see the double black condition where the black, if we delete the black node, it gets replaced with the black. Now, here if you see, the structure is like this, right? 60 sibling is, sorry, the 60 will be sibling. Here it is wrongly pointed to node 50. 60 is the sibling. Sibling is black with one or two red children. So 60 is sibling. Now, can we handle it using just recoloring? Now the problem is if we recolor the sibling to red, right? Like 3.1 case, if we see, right? Sibling was black with no children or both the children black. If we apply that recoloring logic, it will cause the red-red violation. It will cause the red-red violation here also, and it will cause the red-red violation here also. So it will be like it is not solving, right? And if we mark the parent black, then this red-red violation will still be there because 60 if we make red. So that's why the logic which we applied for case 3.1 cannot be applied here. So now that is why this is the different subcase in this delete black node with no child case. Sibling is black, but it contains one or two red children. Now this third 3.3 case, right? Sibling is black with one or two red children. So for now, let's say X is the null, which is the replaced node after delete, because it will be null as we delete the black node with no child, right? S is the sibling of X here. P is the parent of X and S. RC1 and RC2 are red children of sibling S. Now, if you see one thing, depending on to the structure of sibling and red child, we will have four structures. So there will be four subcases in 3.3. Now, let's say if we delete, if the X is on the left side of the P and sibling is on the right side, S sibling is on the right side. So there are two. This is one. This is one. But let's say if the red child is on the left side or red child is on the right side of sibling. So there are two cases, right? So it is right, right, left or right, right. Now there will be one question. Here there are two right children. So why we are considering this right child only? Because for X, whenever we check what type of case it is, for X, we check whether the sibling have farthest red child or not. What is meant by farthest red child? So if we see if the X is a left child of P, then the left red child of sibling will be near to X, right? And the right red child of S will be far to X. So depending on uh, if the X is left child or right child, if X is left child of P, then the right red child of S will be farther from X. And if the X is right child of P, then the left red child of S will be far from X. And we consider the farthest red child if the S have two red children. Why? Because if we consider the farthest red child, then it can be either right case or left case. And it is easy to fix the right and left case because it requires only one rotation. These cases we have understood in our previous videos. So you will remember that right or left requires just one rotation, either the left rotation or right rotation, and it is easy to fix compared to right left or left right case. Right? That's why we consider the farthest red child. So depending on to the structure of sibling and the red child, we perform the specific rotation based on these cases, right? And so for example, here it is a right case. So we perform the left rotation. Why we are doing like this? Because here the black node is deleted, so there is less height here. So we need to balance it out. So we can balance it out by rotation only because we need to bring some node here so that we can balance the black height. Because on this side there are no nodes, so we cannot do anything. We can't do recoloring or anything. So that's why we need to bring some node here so that we can apply recoloring if required to fix the black height, right? So let's say perform a rotation. Left rotation we do in this case. So we know how the left rotation works. Basically, the right child of the P becomes new parent, and the old parent becomes the left child of new parent. And if the new parent had any previous left subtree, then it becomes the right subtree of the old parent. Okay, fine, we did. Now, what we do? We change the new parent color to match with the old parent. Why? Because if we keep this as a black here only, then it will increase the black height for upstream, right? So that's why whatever the black height contribution was coming from previous parent, we need to keep it same for a new parent. That's why we change the color of new parent to match with the old parent. Now we change the old parent and red child color to black. Why? Because we had deleted the black node from here, right here. So there was a black node on this both the sides, left and right. So to balance it out for all the parts, we basically change the old parent and red child color to black, right? So that here for this subtree, it will be restored to the previous black height. And for upstream also, it will basically restore the previous overall black height. So these two steps we apply for each type of case. For left case, we do the right rotation. In right rotation, basically the left child becomes the new parent and old parent becomes the right child of new parent. And if new parent had any right subtree, it becomes the left subtree of the old parent. We basically matched the, now for S, the new parent, basically it already matching the color of old parent. And we change the color of old parent and red child color to black, right? Because if you see here, P was contributing to the black height. So if you move here, then S also need to match. It is already black, but overall for this subtree, the black height was true, 1, 2, right? So that's why to match it, when we move this red child here, we need to make it black to match the previous black height before deletion, right? Which was 1, 2 and null 3, sorry, right? Now here it is right left case. So we need to do right rotation at S because we need to break this zigzag structure and then left rotation at P, right? So now if you do like this, it will become like this. Now the new parent is this. It should match to the color of old parent. It is already matching. And then we change the old parent and red color child to black. Actually, red color child means the right side. So it is already black. So it is not, this is the new parent. It is not red color child, right? So similarly for this, which is a left right case, we do the right rotation, left rotation at S and then right rotation at P to change the structure like this. And this is the new parent. So it should match to the old parent color. It is matching. And then we change the red child and old parent color to black. So red child is basically nothing but the child of S basically, right? Or the child, if suppose S is, if we are doing left rotation, then it will be like basically right child of new parent, right? If it is doing, if we are doing right rotation, then it will be left child of new parent. And if we are doing left right rotation, then it will be basically the left child of new parent, right? And in this case, it will be right child of new parent. So this is handled like this, right? So you can see uh, there are 4 cases comes under 3.3. And what we do basically, depending on to the case, we perform a specific rotation and we basically change the color of new parent to match with the old parent and the old parent and basically the red child color to black. So this is how the third case, delete black node with no child, is handled with different subcases in it. So hope you understood the self-balancing logic in a red-black tree during deletion process. We first understood, we had a quick recap how the binary search tree deletion happens in a standard binary search tree and how it eventually comes to basically physically deleting either the node with no child or node with single child. And using that fact, we understood the different cases in a red-black tree deletion, which is basically three cases: delete red node with no child, delete black node with one child, and delete black node with no child. In a delete black node with one no child, we had three cases, right? It depends on to the sibling, because if we delete the node on one side, we need to basically balance it from the other side. So sibling is the root of other side subtree. That's why we consider the sibling color. Now, depending on to the sibling color, we have three cases under the delete black node with no child. So 3.1, 3.2, and 3.3. And in the last case, we have four subcases depending on to the structure of sibling, which is black, and the red children of that sibling. So hope you understood how the deletion self-balancing, how the self-balancing algorithm works in red-black tree during deletion. If you like the video, please share and subscribe. Thank you so much.